So I would try to set a good example of starting on time, you know, because many of the meetings we have had here, we have been so late all the time. But now we will start on time, and the next speaker is Frank Wilczek. He doesn't need an introduction, so please.
And he's not going to get one, right? All right. Thank you. It's really been a joy for Betsy and me to see this concept of the Feynman exhibit at the museum come to fruition, and through the work of people here and to you, especially Lars Brink, also this conference, which puts some additional scientific meat on it and gives us a chance to see a lot of friends, and I hope also make some useful contribution to the students' perception of what's going on in physics. So without further ado, my subject is there's plenty more room at the bottom. In 1959, Feynman gave a famous after-dinner talk called There's Plenty of Room at the Bottom. And I will begin, that's the context of this talk, of course. I will begin by giving an annotated version of highlights from Feynman's lecture. Then I'll talk about different ways in which there's plenty more room today. There's still plenty more room at the bottom. There's plenty more room in Hilbert space. There's plenty more room for a tiny industry. There's plenty more room for time. And there's plenty more room for intelligence. So I will talk about those subjects in that order. So first, Feynman's lecture. It's become legendary. It was given in 1959, but saw far ahead. His vision was that there would be technologies that work at the molecular level that would be important, and he had ideas about how to do them. The fact that such a distinguished physicist would dare to say such things at a time when I remind you computers, which are much less powerful than our iPhones today, filled enormous rooms and generated a lot of heat, had fans and so on, and were very painful to use. He was thinking about something that resembles today. The fact that he would go so far out on a limb made it seem incredible that these things could be done, and exciting because he showed you how they might be done, that you could do big things at that scale. Little joke there, big things at that scale. You could. It's still fun to read. If you haven't read it, you really should. It's fun. It's not technically demanding, although there's a lot of depth to it if you want to follow up all the leads, and in fact, it still hasn't been fully mined. You can also find online, so it's free, a later version of this lecture called Tiny Machines, where you get to see Feynman in action talking about these things with this slightly later perspective. This was, I think, a talk at one of those famous EST conferences. TPORATB, there's plenty of room at the bottom, contains many inspiring images and visions. And so by way of introduction, and because it's fun, and to set the context for what comes later, let me just mention a few. So one of the big points of there's plenty of room at the bottom is extremely simple and yet extraordinarily profound. It's simply the message that atoms are really, really small. But saying that doesn't seem very impressive. And Feynman had a way of making it much more vivid and powerful by talking about how you could put small images so that the different characters barely take a few atoms on a side, so they're barely discernible at the atomic level. How small would that let you get? And he said that you could put the entire 24 volumes of Encyclopedia Britannica on the head of a pin as images. And you could fit the entire Caltech library on a library card. Then he went on from there to say, suppose you didn't want images, but were content to just encode the information in zeros and ones the way we do today. And you imagine that you could encode a binary digit in something that contained 10 atoms on a side. And then you could put all of mankind's information output in a speck of dust. So all the books that had ever been written, all their information content, not the pictures, but the words, into a speck of dust. I don't know if that still holds true. I didn't check the calculation, but probably you could at least put Wikipedia in a speck of dust, and that would be almost as good. So that's a kind of humbling thought, in a way. So this is Calvin, of Calvin and Hobbes, screaming to the universe, I'm significant. Scream the dust speck. So that's all of human knowledge is a speck of dust. But you can also read it the other way. You can also read it the other way. I think this is really profound and a sort of antidote to this cosmic insignificance, is that if we look within, we contain multitudes. Many, many atoms, enough to support lots of complexity, lots of thinking, lots of structure. So the fact that we can contain many specks of dust means that we are also a universe, each and every one of us, in ourselves. Another image that was very vivid coming out of this lecture was the idea that you could have hands that would build smaller hands, that would build smaller hands and smaller hands. And this was one way he envisaged working on atomic scales eventually. And here it is in reality. And here it is, we wanted to stress the union of art and science. Here it is made visual, with a visual impact that's also very profound and accurate science. This is the Sierpinski triangle, a famous recursive structure that makes a fractal and has the same structure. If you look at a small piece of it, it has the same structure as the original. He also had a concrete challenge. He actually had two concrete challenges that he posed as projects for people to try to do, one of which was to make a rotating electric motor that could fit into 1/64th of an inch cube. And that caught the imagination of a graduate student at Caltech, an alum of Caltech named William McClellan. And within a couple of years, he did it. And you can see this very motor at the Art and Science Museum at the exhibit. And here's a nice picture of that thing. I think in the background is some kind of flashlight, because you can see the shot. It seemed kind of mysterious. Well, anyway, this is a picture of McClellan and Feynman looking down at his motor. And this is kind of a lineal descendant of that kind of idea. These are tiny motors, even smaller than that. They're not self-contained electrical motors, but I just wanted to give you a sense of the kinds of things that people can do now on those kinds of scales. These are motors that are driven by ultrasound and directed by magnetic fields, so you can imagine things floating around in your bloodstream or doing useful things inside fluids with these little gadgets. Another extraordinary image that Feynman actually attributes to his friend Al Hibbs is the concept that you could swallow the doctor. If you had a small enough doctor, you could swallow them, or more realistically, small enough medical devices, you could swallow them, and if they were intelligent, they could navigate around your body, get to inaccessible places without sawing you open, or things like that. There was a movie based on this called Fantastic Voyage, which totally mangled the science, but was inspired by it. This is a kind of science fiction-y image of what they look like, but this is now real. I mean, these kinds of devices are now quite real. This is used to do endoscopies without the horror of doing an endoscopy. You swallow this little pill, which is the size of an American dime, roughly, and it has lights, batteries, antennas, everything you need, and can be steered around. He also emphasized the importance of imagery for addressing fundamental problems of biology. You know, what do proteins look like? Tells you a lot about how they work and what they do. If you want to know what the genetic code is, you just look at the DNA and read it out. That was his vision. And of course, biologists now have a wide variety of tools to look at things. And this is something we'll come back to, a ribosome. And you see it's very, very complicated. But if you look at enough of these things, you can discern structural motifs. And these different colors are things like alpha helices and beta sheets and other structural motifs that can be decoded to figure out exactly how this thing works. And several Nobel Prizes were awarded for figuring out this and techniques for visualizing things, very much along the lines that Feynman outlined. He also said, why can't we drill holes and cut things and solder things and stamp things out and mold different shapes all at an infinitesimal level? Why can't we do manufacturing and put chemical synthesis out of business? Just make it, and make the materials. And this is an artist's impression of what Feynman had in mind. Nothing like this actually exists, but it might someday. As you'll see, the real molecular machines that are out there look quite different from this, but you can see the hands within hands within hands, and you plug it in and put in the instructions, and out comes whatever molecular complex or structure you want it to make. Another one that still is futuristic, but I think fascinating for physicists to think about, is can we emit light from a whole set of antennas like we emit radio waves from an organized set of antennas to beam the radio programs to Europe? So, for instance, nowadays we know how to program light arrays we could change their phase relative to each other. We could simulate Hawking radiation if that's what you want to do. Simulate motion towards the horizon. Or, as I learned about just last night, Professor Pan has managed to make different wavelengths of light interfere with each other. Anyway, this is, in simple cases, something that people do. So-called phased array is now a realization of Feynman's dream there, and there's a lot more to be done with these things. Anyway, if you go to Wikipedia and look up phased arrays, you can find a really fascinating subject in the making in physics. Okay, so that's my quick recollection of some of the most striking and suggestive metaphors, ideas, and inspirations that are in Feynman's lecture. There's much more, and I strongly advise you to look. But now I'd like to talk about things that he didn't manage to envisage almost 60 years ago. The rest of the world has caught up to a lot of it and even gone past. But for students and the future, it's wonderful, and I'm sure Feynman would be delighted that he didn't think of everything, and there's plenty more room at the bottom. So one thing that actually he did think about, but a little bit later, is that there's plenty more room in Hilbert space. That's a technical way of saying that quantum mechanics is very big, not in terms of size, it's not very small things. I would like to say it's very dense, not in terms of mass, but in terms of information and the structure that it reveals about the microworld. Now, all the way back in 1929, Paul Dirac, who, as we've heard many times, was one of Feynman's great heroes, said, this was when quantum mechanics was still pretty new and untested, but Dirac had a lot of confidence, for good reason, in this framework. He already said in 1929 that the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. And the difficulty lies only in the fact that application of the laws leads to equations that are too complex to be solved. Well, our standards for what's too complex to be solved have changed since then. And one of the great frontiers is to deliver on this promise of Dirac by actually trying to address the equations of quantum mechanics directly to get their consequences for the structure of matter, and to use them creatively to design new structures. Feynman put it a little more forcefully and directly. He said, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. So he was beginning to think about and talk about quantum computers at that time. As I mentioned, the way I like to talk about it is that quantum theory reveals that the world is a much denser place than anybody imagined before quantum mechanics, not in mass, but in structure and information. Let's make that more concrete to get an idea of what we're up against when we try to solve quantum mechanical problems and why it's difficult to do on classical computers. So consider, for example, how we describe the state of just two particles. In quantum mechanics, we have to specify a wave function, which is, roughly speaking, any complex function. It should be square integrable and so, but basically any complex function. Classically, it's a very, very restricted class of functions. It's just the sum of two delta functions. So the quantum mechanical description is vastly more complex, and even a simple atom can support very complex behavior. Or, coming closer to computers, consider how we describe the state of a 3-bit register. So the different bits can be either up or down, or zeros or ones. And there are 8 of them, if we have 3 bits. So in classical computers, when we have a 3-bit register, we have a choice among 8 points. That's the space that describes their state. In quantum mechanics, we have the amplitude for each of these things to occur, which is a complex number. The sum of their squares has to be equal to 1. And if you think about it a little bit, you'll realize that that means you have a point on a sphere in 16 dimensions. So instead of 8 discrete points, you have, in the quantum mechanical description of the same thing, a point on a sphere in 16 dimensions. And if you go to more bits, the spheres get bigger and bigger, much more rapidly than just proliferating points. That shows you why it's complicated to describe quantum mechanical systems, but also why they have enormous density of information, potentially. The ideas of quantum cryptography and quantum computation are aimed at exploiting this vast internal territory. In view of the time, I won't go through the details of how quantum cryptography works, but basically the idea is that measurement collapses the wave function and so destroys some information. So if you send quantum mechanical information stream from one place to another, you can tell if somebody measures and has destroyed some of the information, and then if they haven't, you know there's no eavesdropping been going on. See, Eve is the one who does eavesdropping. It's a little joke. And then you can have security for the transmission of the other bits. And this is what a superconductor. This is what Google, Microsoft, IBM, all the giants of computing are trying to protect their business models and extract money from the federal government by building quantum computers. And this is Google's quantum computer based on superconductivity. So whether you have a unit of flux that points up or down, and a little Josephson junction is the basic qubit architecture, or it could be a little cavity. When you see these quantum computers, you should realize that mostly this is refrigeration. The actual business parts are buried deep inside. And that's why all these computers based on very, very different physical principles look pretty much the same. Here's Microsoft's quantum computer, which is based on anyons, based on very interesting physics, which is why I'm especially mentioning it. Anyons are different kinds of particles, different from bosons and fermions, which are a relatively new concept in physics. And they have the property that when you wind one around another in physical space, you make complicated motions in Hilbert space. And so you can manipulate that vast store of information that's potentially in Hilbert space by moving the particles around. And that has big advantages because the result depends only on the topology of how these paths wind around each other. And in topology, you can't make small mistakes. It's immune from small mistakes because small mistakes don't change the topology. And so these kinds of computational strategies, if they could be implemented, would be much more error protected. The problem is that it's very difficult to make these particles in the first place. So there's a race with different strategies being explored. It's a pretty picture to think about computing with knots. That idea goes back to the Incas. They computed with knots, but they were doing rather not quantum mechanical knots. They were doing simple arithmetic but knots can get very complicated, as you can see, as you can easily experience if you comb your hair without enough care, and the quantum mechanical wave functions directly reflect a lot of that complexity. So the way you do computations is do manipulations in space, and the wave function reflects what you've done. So the computation gets done by encoding the structure of complicated knots. Another beautiful idea that was mentioned in earlier discussions is quantum simulation. This is using well-controlled, well-characterized systems like cold atom arrays of atoms trapped in optical lattices, so trapped by crossed laser beams to make a lattice, or arrays of ions that can be addressed using lasers to make operations on their states. And in this way, you can sort of tailor your own Hamiltonian. Physicists would know what that means. You can analyze model interactions using systems that are very well characterized, so you know what they're doing, and if they have an accurate model of something that you'd like to know about, you can use the simulated version. So it's the same kind of strategy as a wind tunnel. These are like quantum wind tunnels. This is Misha Lukin, who's a great experimentalist at Harvard, and he has a 51-qubit quantum simulator based on the strategy of charged ions and addressing them and doing gate operations using lasers. And this is an artist's impression of a cold atom optical trap simulator. There's a lot of room for creativity here. So you can have spins, you can have them in different places, you can apply magnetic fields, et cetera. You can change the density, et cetera, et cetera. And so you can, for instance, hope, and there are proposals to simulate nuclear matter, to simulate anyons. That's actually been done. And to simulate the Hubbard model, canonical models of condensed matter physics, using this kind of strategy. And young people, there's enormous room for creativity here because you can use different kinds of spins. You don't have to use all of one atom. You can put them in different internal states, and so you can make them three-dimensional. So, I mean, it's easy for me to say those things, but yeah, with enough work, you can hope to do those things. And as I mentioned, in this way, there's been quantum simulation of this funny anyon behavior that particles keep track, the wave function of particles keep track of which way they've moved, their histories in space, and how those get entangled. So that's my quick and I hope stimulating sketch of what's going on in the show that there's plenty more room in Hilbert space. Now I'd like to talk about the plenty more room for tiny industry. Feynman's hopes for information storage that I mentioned, putting the Encyclopedia Britannica on the head of a pin, or encoding information so densely that you could put the whole world's library in a speck of dust, have more or less been realized in modern computers. You can do those things. However, a large part of his lecture was about micro machines and micro manufacturing, and that remains futuristic. But not so futuristic that it's hopeless. There's an existence proof, and many elements are in place. So the existence proof is us, is biology. Biological manufacture works at a molecular level and does very, very sophisticated things. Biology is wonderfully good at making tiny, chemically powered, programmable machines. The strategy is several parts. DNA and RNA are the information storage molecules and the information transmitting molecules. And here's a little sketch of how they work. You start with DNA, which famously has a four-letter alphabetic code with redundancy. And then the RNA transcribes the message without changing it, so you have that remaining. And then the transcript gets translated from information to a physical form, a protein, at the ribosome. Ribosomes, which I showed you a picture of what one actually looks like, are manufacturing plants. So the RNA comes in, and the protein, the amino acids, come out. There are also transport vehicles and highways. The microtubules, which are proteins, so they come out of these ribosomes, and you build the microtubules are, I think I have a picture here, stacks of two proteins called alpha and beta tubulin, and the microtubules can grow or not depending on external conditions, but they form, if they attach at some end, they can form like skeletons inside cells. So cells need skeletons too. They're not just blobs of protoplasm, the way I was taught in biology. But they can also be retracted, and they can grow and move into and change direction and so forth. So they're very flexible. And kinesins, I'm not sure how this is pronounced. Kinesins probably, are beautiful little objects, beautiful little proteins that carry cargo, like this. And that's sort of what they look like. And usually they go from the origin of the microtubule to the outer edge. That's called the negative to the positive side, or out. Although some have recently been discovered that with some help can move in the other direction too. It's biology, every rule has exceptions. This is a little more realistic picture of what it looks like, and here is a little more realistic version of the motion, and here is the real thing. And it's a great problem, by the way, to look at something like this and figure out how it works. If you didn't know what it did, could you figure it out from this? Or the ribosome, could you figure it out? That's a really interesting kind of question. Or better yet, could you design it yourself? Design new ones that do tasks that you'd like to do. Nature kind of stumbled into these things by evolution, but not all paths were explored for sure, and not carefully optimized either. Now, to do this, we need enabling technologies to do this micro industry. And it's important, it's beautiful and true that a lot of the tools are in place. Scanning technologies, the scanning tunneling microscope, atomic force microscope, all these kinds of things, nitrogen vacancies, which I'll mention in a moment, allow us to access molecular scales. They really do, in a way, in a very real way, realize Feynman's dream of just look at it. You can just look at the surface of a substance and read off its atomic structure and things like this. This is one way. This is the so-called nitrogen vacancy. You put little nitrogens inside nanodiamonds, so all the carbons, you diffuse a little nitrogen in, they replace a carbon and also make a vacancy. There's nothing unique about that, but it turns out nanodiamonds are very cheap and they're very reproducible, and so this gives you a molecular complex which has been very well studied, and you know the spectrum and you know how it responds to different perturbations. So it's a very sensitive way of probing the properties of matter. This is again from Lukin's lab. He has a very vigorous nitrogen vacancy initiative. And this was actually, the way I learned about it, this is the discovery paper for time crystals, which happened to be in a bunch of nitrogen vacancies when you put several of them together in a nanodiamond. And using them, you can probe, for instance, the properties of materials. You put your molecular complex there, your nitrogen vacancy. Since the nanodiamonds are really small, you can place them very precisely, know where they are, adjust their distance. And they're sensitive, and they can be sensitive to all kinds of exotic properties of the matter underneath, or not so exotic properties. You just scan and see aspects of the molecular structure, the magnetic fields that are generated near the surface, and so forth. This is the same idea that for the slightly more mature technology, the scanning tunneling microscope. Here you have a tip that can come very close to a surface, so close that the quantum mechanical process of tunneling is possible. But tunneling is very, very sensitive to the exact distance and the exact properties of the material. So when you scan over a surface, you can make a topographic map representing different, or several topographic maps representing different properties of the surface underneath. So you can see where atoms are sticking out electrically, where the patterns of magnetic fields are, and other things. And then in 1986, Don Eigler at IBM noticed that you could also push atoms along with these scanning tunneling microscopes, and made a famous ad for the company that employed him, which you see here in atoms. And you'll notice, by the way, that atoms have wave functions. They're not points, and that's why they show up in this way in a scanning tunneling microscope picture. And I wanted to show you this world's smallest movie, which was made at IBM. You can see the wave patterns. So the atoms disturb the surrounding material according to quantum mechanics. And with enough work, you can make silly movies of individual atoms. Yeah. It's not long. Let's just watch the whole thing and enjoy it, since they work so hard to do this. Okay, so that's the world's smallest movie. Very exciting is a slightly different kind of scanning technology, because this one is mechanical. This is the so-called atomic force microscope. So you have a cantilever, and it gets attracted or not to the sample, and you can scan and see when things are sticking out, and translate that directly into mechanical motion or electrical signals. So if you're thinking about making a factory on an atomic scale, this is probably a really good thing. So those scanning technologies let us look at and manipulate things on a molecular scale. We also have a different technology on a different scale, but somehow related spiritually, that's rapidly emerging as very powerful, 3D printing. This makes the idea of programmed manufacture. So you have an idea, you translate it into digital form and make a material. Then the materials are precisely characterized because they're the realization of a program. These are demonstrated realities. And again, at the Science Museum, in the shop, in the gift shop, they sell these things, and you can also watch them being made. And you can make very elaborate shapes. You can really, within large limits, as long as you don't want things that are too small, you can order them and make them. But molecular scale human manufacturing is still slow and unsophisticated relative to biology. The biological machines, which you saw, like ribosomes and kinesins, don't look at all like human machines that are kind of blocky and typically metallic. So there's a great challenge in engineering and chemistry to realize the potential still of molecular scale tiny industry. I'd like to say just a few words about plenty more room and time, because this somehow is something that Feynman did not mention, but is very beautiful and important, and is also possibly something you'd like to use micro-industry for, to make really good small clocks. This is the world's most accurate clock at present, and it's from NIST, the National Standards and Technology Institute, and it's based on ytterbium. I think this is still the world's best. You have trapped, again, almost everything you're seeing here is plumbing, but inside there's an atom that's trapped in a magnetic field and vibrates. Its internal state vibrates at a very precisely known frequency, and that's the standard to which you can lock other things to make the world's most accurate clocks. This is a not so accurate clock, but has the advantage of being really small. This is an atomic clock on a chip. Now, I'll quantify now how accurate these things are. It's really quite mind-blowing. The best present-day atomic clocks, like the one I showed first, are accurate to about a part in 10 to the 18th, which corresponds to roughly 1 second over the lifetime of the universe. The chip-scale atomic clocks are accurate to about 10 to the minus 13th. Now, why in the world would you want to make such accurate clocks? Well, there are very good reasons. GPS technology, which can't translate time into position because it's all based on the speed of light, knowing where you are. And so that's why you want these guys on a chip. You can carry them around, and if they're better, you can get more accurate locations. The Department of Defense is very interested in those things. For scientific purposes, accuracy is even more at a premium because you might want to keep interferometers aligned, for instance, and then the tolerances are like the wavelength of light, or you might want to keep accelerators aligned, and you have to know positions very, very precisely. Or for triggering the optical arrays we talked about. You have to get very precise timing to make the interference work right. And that's why DARPA is funding time crystal research. Time crystal, basically for this purpose, is just saying instead of one atom, you have many atoms that have characteristic frequency, and then you can increase the accuracy. Okay, so finally, am I using the time? I have what? Plenty more time. Plenty more time. So plenty more room for Blather. Okay, plenty more room for intelligence. Self-reproduction, development, and connections. This again is something that Feynman sort of goes around the edges of, but doesn't quite get into. So now we have artificial brains that have many advantages over human brains. They're much faster. Okay? They're based on exchanging electrons at high voltages instead of chemicals at low voltages, and so they're much faster. If you quantify how long a synapse versus a computer chip, the speed ratios are like 1 billion. Also, if you compare, say, it's hard to say what the speed of thought is. How long does it take to have a thought? But one measure is, suppose you're watching a movie that's a sequence of stills. How fast can it be before you, or how slow can it be before you recognize that it's a sequence of stills rather than continuous? And it's about 40 frames a second. That and several other measures indicate that the speed of thought is about 40 thoughts per second. If you ask how fast people can play the piano, if they don't know, that's also roughly the same kind of thing. The computer chips are much smaller. All right? I'm always mortified when I am beaten at chess by some chip that's like this, like somewhere deep in here that you can't even so you can make many, many units of computation in a very small space. They're stable. They don't forget unless you put them in a magnetic field or pour water or do something horrible. They're very good at remembering. They don't need to be fed. They don't get sick. They don't die. That goes into the duty cycle also. They don't sleep. They don't take time for social activities and they don't die. And they have an open architecture. If you want to add something to them, since you know how they work, you can add the module. So if you wanted to see ultraviolet, you put in an ultraviolet camera and a little firmware, and you're there, for instance. So they have an open architecture. Since you know how they work, you can interface to them. So why aren't they smarter? Well, human brains have some advantages too. They have a three-dimensionality in a way that ordinary computers don't. The ordinary computers are based on chips, and of course you can stack chips, but the interlayer connections are much slower and sparser than within a layer. We have self-repair. We can fix damage within certain limits. Whereas computers, famously, to build one of these chips, you have to have a clean factory that costs billions of dollars and eliminate all dust, and people go around with them in exotic costumes so that they don't contaminate, and still most of the chips aren't good and you have to throw them out. And then, of course, if you scratch the disk, and so it doesn't fix itself. Humans have integrated sensors and actuators, also known as eyes, ears, arms, fingers, legs, that are very, very good, that people have not yet been able to emulate with the same capabilities in computers. We've had billions of years of evolution to get these things. And they're very, very, another part of the other side, if you like, of this question of modularity is that they're not modular. They're really integrated in, but the integration has been honed over time and is very, very good. And human brains, human nerves have enormously more connectivity than microelectronics. Human neurons typically have thousands of connections to other neurons in very complex patterns, whereas on chips you have very many fewer connections in very regular patterns. And humans learn by doing, that is, using these integrated sensors and taking advantage of the connectivity, as I'll show in a moment. That's a very powerful strategy for getting to be a powerful mind, to interact with the world, take in what it has to offer, and internalize it. So how does that work? Well, recent developments in computing, in particular the success of deep learning in pattern recognition and game playing applications, the famous ability now of computers to recognize cats in pictures and to play Go and chess better than any human, have illustrated the power. That's less impressive. Have illustrated the power of neural networks. Neural networks, of course, as the name tells you, were inspired by human brains, but the actual neural networks are, compared to human brains, much, much smaller and less connected. But the basic strategy is you have neurons which either are responding to the external world or getting input from other neurons and firing if certain linear combination of these signals exceed a threshold condition, and then you keep doing it layer by layer until you get an output and read out the final firing pattern. Here's a little more impressive-looking, scientific-looking version of the same thing. These networks, it's important to emphasize, are not programmed in the usual sense. No one says what the connections are. No one says, lays out a series of commands that the thing is supposed to be doing. What it does is just take the signal and propagate the thresholds through until you get an output. They learn by experience, depending on whether they get a good match to the thing they're supposed to be reproducing or not. they encourage or discourage the pattern of connections that led to that result. They learn by adjusting the strength of connections. So all their information is stored in the strength of these connections, and that's how they learn. So having more connections, having richer connections, and having different varieties of connections that just don't go from one layer to another, but loop back and things like this, is what brains have that neural nets don't, and very plausibly is the key to making human brains and animal brains more powerful in many respects. If you've ever watched a baby learn, it's very instructive. We just had our first grandson recently. It's fascinating to watch how they look at their hands and play around and decide how to do things and learn to walk. It's not because someone tells them to do it. They interact directly with the external world. They learn by sculpting patterns of connections inside their brains. And a kind of proof of that is that human infants very quickly grow a full complement of neurons. Adults grow very, very few additional neurons, maybe a few in the hippocampus and a few other places, but basically not. You don't want to keep growing neurons because if the wiring pattern has the information, you just screw things up. And an overabundance of connections. They're more connected than they're ever going to be very early in life. And the way they learn is by pruning away connections that aren't so useful, that aren't leading to successful results, and reinforcing ones that are successful. Very much like artificial neural networks, but with more connections and probably additional algorithms. And the big point is that the emergent structured hardware is its own software. There's no separate program. It's all stored in the connections. To get an idea of the richness of the scale, this is a beautiful drawing. We talk about the intersection of art and science. To me, some of the most beautiful artistic objects are scientific objects. This one is by the great neuroanatomist Raymond y Cajal. It's the optic spectrum of optic tectum of a sparrow. So not Einstein, not Feynman, not a super powerful brain, but you can see it's very, very connected and has various kinds of elements. It's important that this is a Golgi stain, and it's a section, so every word counts. It's a section means it's a very, very thin slice, basically only one cell layer thick. The Golgi stain means that only about 1 in 100 neurons get stained. The miracle of the Golgi stain is that it stains. It's like a quantum stain. It either stains completely or not at all, and it stains about 1/100th for reasons that still aren't understood. And if you look at a more unprocessed version of a neural net, you see the cell nuclei. So and the neuron has each cell nucleus has all these connections coming out of it. This is what a less processed version on a more magnified scale looks like. And it's a really, really dense web of connections way beyond the simplified neural net architecture that are embodied in deep learning. So present-day engineering has no real analog of the biological development process, which is based on two very powerful ideas. One is self-reproduction. So the cell can make another cell that's fully capable, but also as it's reproducing, it changes the DNA in subtle ways to make modifications in the instructions. So different kinds of neurons can be made. And then that's how the development process occurs, and that's how you get, so that because of the miracles of exponential growth, when you have self-reproducing machines. You can have many, many neurons and many, many connections. And that enables this powerful strategy of learning by doing, by sculpting. So there's plenty of room to do better, I think, by pursuing these kinds of engineering initiatives. So let me summarize. Well, actually, that was the summary. There's plenty more room to do better, so go out there and do it, guys. All right. Okay, thank you.